Okay, good afternoon, everybody. It's Nigel Watts here from our offices in Malaysia, in very warm and humid Malaysia, close to the equator. So today, I'd just like to welcome you to our flat slab webinar. I'm going to be taking you through our session today. And we've just got a few more attendees who are joining us, so we'll just give it a few moments. Just as a precursor to starting, if during the course of the event that you have any questions, please feel free to write them into the chat. We will attempt to answer some of those questions during the session. I will not get to see this. I will not be looking at this until the end, so I'll try and explore some of those questions with you at the end when we wrap. Okay, so I think let's get started. Just wanted to give you a little bit of background on Prota and on us, and I'm just going to give you some oversight. I will turn off my webcam in a minute, and then we can focus more on the presentations. But just to start with, Prota has been around for, oh gosh, well, 35 years now. This is our 35th anniversary this year, and we are a specialist business focusing on engineering and consulting practice, and also software development, as obviously you would realise with attending today's presentation. We're an interesting group of companies, so we're just not developing software. We also have a very large and successful engineering practice, which I'm going to talk about, and we do deal with other businesses. We have a computer business which distribute software like Autodesk, an architectural practice, and we have the other businesses globally that form parts of the larger Prota group. So Prota Computer is also an interesting business of ours. We have a very close relationship with Autodesk, which goes back over 30 years, and we are the largest Autodesk distributor in the Middle East and Eastern Europe. So this allows us to sort of keep abreast with what's happening in industry, particularly with Autodesk, as it is one of the biggest players in the AEC market. The engineering side of our business is also very interesting. We get involved on really interesting projects all over the world. So we not only develop software, we also are consulting engineers, and we deliver a range of interesting projects globally. And that covers a range of different industries, so not just building design, but we get involved with transportation, in heavy industry, especially high-rise, complicated high-rise structures. And we have a lot of expertise, particularly in seismic design, as well as BIM technology. And some of the interesting projects that we've been involved with over the years, the Warsaw Metro line, in Poland was an interesting job. We've done almost all of the metro lines in Turkey. We're one of the biggest providers of design services there. And recently we were also involved with the new international airport in Istanbul. So there's some interesting range of mix of jobs that we've been involved with. And so this has kind of helped shape the way in which the software has developed over the years as well. So it just gives you some insight into what we're doing in practice, and you can see that we're also delivering projects just like you. So there's an interesting timeline for what we've been involved with. In fact, as I mentioned, the office started back in 1935, and we started commercializing software in the early 90s. In 2000, we had what was then the global release of a product called Ryan. And so we commercialized the software which we had developed in-house in the early 90s, and it's culminated with a product called Ryan, which was released in the early 2000s. We were one of the first to introduce bidirectional integration with Revit, being a physical modeling system. We started this process back in 2007, and we continued to develop that platform for many years, but then in 2015, we redeveloped the entire suite of products, which became known as protostructure. And this has evolved tremendously over recent years. And we're now in a position where we're starting to, we're in a process of completely redeveloping a whole platform, which is something that we're very excited on and we're going to be launching very soon. So watch this space. So we've got about 300 people on the design and development side of our business, and we support a range of interesting businesses across the world. So I think there's over 10,000 people using our platform on a daily basis, and that's supported directly by us and our really valued partners in over, I think, 17 countries now, if I'm not mistaken. So we are headquartered in Ankara in Turkey. We have other global offices around the world. We're also expanding. At the moment, we're looking at establishing offices into Berlin, and we're also in the process of setting up in the Philippines. So it's a really exciting time to be part of the Prota group. Now today I'm going to be focusing on two solutions. One is protostructure and the other is protodetails. And just a little bit of background on those. Protostructure is what we would call a focused BIM solution for concrete and steel buildings. And what do we mean by that? Well, we're working with physical models. We're developing physical models very quickly, and from there we can automate a lot of the analysis and design, which could typically take you a long time. We're automating that to the chosen codes of practice, and we're then synchronizing this with our protosteel and protodetail platforms for producing all your drawings, okay, all your concrete work, all your steel detailing, even right down to connections, even down to fabrication detailing is being provided. And being a physical model, we can easily communicate that with other platforms. Now, I think people like it because users tell us that it's easy to use, and it also helps with driving productivity. Now, sorry, I'm getting some messages. I think you can see my screen on the side. I don't know how to minimize this. Okay. Now we're also going to touch on protosteel today. So this allows you to just create all your detailing with one click. It's a complete CAD system. You can also edit within the protodetails environment. All of this can be done very easily. And here's just a snapshot of some of the output that protodetails creates. Now, just give me a second. I know you can see my screen on the side. I'm just going to kind of maximize it, and then I'm going to try and minimize my screen again and see if you can't see it. Okay. All right. Hopefully that's hidden it. I'm getting messages from my team here as we go. So today, this topic is on flat slab design and protostructure. Now, what do we mean by flat slab design, and why flat slab design? Okay. Well, perhaps you can tell us what that might be for you. So that may be related to reduced structural zones within your developments. That might be to comply with stringent building envelopes and trying to maximize space within developments. It may be to provide flexible internal arrangements where the architect wants a free hand at how partitions and so on are provided within a building. Maybe just to give it a slick visual appearance, again, an architectural requirement. It may also be for construction, and you may be wanting to erect buildings quickly. You want to minimize the amount of formwork that you're using during construction. You may want unobstructive service zones. Okay? And there may be even a requirement to accommodate more irregular column positioning. Again, there may be other architectural considerations. So whatever it is, for whatever reason, we're certainly seeing more and more flat slab systems being used in practice. Now, what do the codes say when it comes to flat slab design? Well, if you review both the Eurocodes and the British standards, you may know that there's what we would call a simplified method for being able to design a flat slab structure. And that looks at creating an idealization where you would look at identifying your column strips and middle strips. You can then build up a simple subframe as you would with any other, say, general analysis software for beam and columns as a simple model. And within this, you would cater for things like pattern loading, and maybe you're also considering moment redistribution. Okay. And then what you would then do is take those resulting forces between the column strips and the middle strips, and you would distribute those empirically. And the code provides guidance on this. So in a very simplistic way, I could take a scenario here where I've got my column strip, my middle strip, and we would then create an analytical model. We would load this up with the loads that were applied across these zones. And the code then would give you ratios in which you would proportion them to your sagging moments and your hogging moments, and between your middle strips and your column strips. So the code would provide guidance on this. And if you referred to the BS and Eurocode standards, you'd see that there's guidance available. Now, this is really actually an idealized approach to what is done with FE models. So what they've done with the code is taken what might be a real life situation using finite element analysis and creating a more empirical way to do that. But what about irregular arrangements? How about if your model's not a square box and you've got irregular arrangements that you need to consider within the model? So this is where finite element comes in, and obviously as practicing engineers we're having to increasingly deal with larger and more complex models. Okay, and finite element analysis is really the only practical way in which we can effectively deal with these scenarios. Now, there's three main considerations with flat slab design that you need to be aware of. Obviously, deflections is a key consideration, and treatment for those within the analysis and design process. Bending in relation to area of steel and localized design, which I'll get to. And we also need to consider punching shear as well as local bearing. Okay, so these are probably some of the key considerations that you'd need to be aware of as you're designing a model of a flat slab project. Now, I think the first place that you'd want to start looking at is with the analytical model properties. Now, one of the key considerations is deflections, and for the analysis model, we need to think about a number of things. And one is what appropriate member or section properties to use. Okay. Now, the British and Eurocode standards suggest consistent properties, but is that correct for deflection? Now, if we do look at this in more detail, we would know that in general, deflections for flat slabs or any concrete structures should be regarded as estimates, no matter what type the analysis is. And this is largely due to the material properties with which you may consider. Now, if I just took a typical grade of concrete, say grade 40, for example, your E value may vary quite significantly, and this can be very due to maybe construction methodologies, perhaps the times that you're striking your reinforcement, the quality of aggregate and materials that you have on site. There's a number of factors that can affect your E values, and this in short also has an impact on deflections. Now, the stiffness, so what we do have to do is modify the stiffness to allow for this, and in particular we need to allow for both creep and for cracking. So what do we do? Now, there's been research done in this area, and one of the reports I would point you to is a Syria report 110, and this is the design of reinforced concrete flat slabs to British standards. You can also refer to similar guidance with the Eurocodes that gives you some guidance on adjustments that can be taken for allowing for creep and shrinkage. Now, in simple terms, this suggests reducing your E value or your modulus of elasticity by up to half to 2/3 to allow for creep, and then also reducing your I by half to allow for cracking. So in effect, what we're doing is adjusting your EI value or reducing your EI value by a factor between 4 and 6, and this would typically relate in reducing a stiffness between a final stiffness of between, say, 0.16 and 0.2 will be applicable. And this is the type of guidance that we can follow within Prota structure, and I'm going to talk a little bit about this as we move through. Now, obviously also, in addition to deflections, we also need to consider bending. Now, the code guidance that I talked about earlier is great for regular slabs, but it breaks down for irregular arrangements, as we talked about. And there's two ways in which we can deal with bending. One is that we can look at area of steel contours using finite element analysis. And we can also interrogate or interpolate those contours to give us some sensible design values. And one of the ways that we do that is with integral strips. Now, if you're familiar with the code, you'll realize that when you have things like columns and positions, you'll realize that as moments approach the columns, they will peak. And the code has provisions to allow you to average moments across those peaks. You don't need to take the full values. And typically for a column zone, you will have an inner column strip and an outer column strip. And code guidance typically allows you to look at the spans, typical spans between columns, and integrate across those column zones by taking those spans and looking at 25% of that span across the inner column strip and 12.5% either side of that. So in effect, what we're doing here is we're averaging out the moments across our column zones to provide us with a more economical and reasonable design based on code requirements. Shear is also important, and in the software we will be checking for both local bearing as well as at critical parameters. So what I mean by critical parameters is that code within the software will check for both locally beneath, say, a column or wall, and we will check based on code requirements at 1.5D or 2.5D if you're using Eurocode, and other codes will have guidance as well. And it will check those zones for shear. And if we find that shear is excessive or exceeds the code, exceeds minimum capacities, then you may need to provide additional shear steel. Now that can be provided in a number of ways. So you can mitigate this by maybe increasing the longitudinal bars that you provide within the slab, or you may wish to increase or add in shear studs or links. You could also mitigate this with local thickenings. For example, you may wish to include drop head panels and the like. So there's different ways in which punching shear can be considered. Now, there are also separate considerations for edges versus maybe internal columns. So if I have columns that are sitting on an edge or on a corner, the way in which these are looked at is different from how we would treat an internal column. And you may also need to provide local consideration for, in particular, walls. And with walls, you can have local stress concentrations within the wall due to localized bending. And there may be times where you need to look at this independently. So we will take the shear forces, and the code will require us to make adjustments to calculate an effective shear force. And this is called VT. Now, depending on the scenarios within the software, we will make these adjustments for you. So maximum adjustment to the British code is for corner columns, where it's 1.25. And you can see here that there's quite a horrendous formula to the Eurocodes here, where magnification factors will be adjusted depending on positioning as well as openings, and that can be anything from 1.15 through to 1.5 for corners. Okay, so in the software we will make these considerations, and we will adjust our shear forces to cater for both the shear and bending, local bending at those joints in different directions to calculate our effective shear force. Punching shear parameters are also an important consideration. So as I mentioned, you can have different parameters depending on where you are. Obviously, if you're on the edge of the building, you would check for parameters on the edge, and on corners again will be checked. And we will automatically look at calculating these and providing effective parameters for checking. Now, the final consideration within flat slabs is, or another very important consideration, is the introduction of openings. So you could have openings adjacent to columns and column zones, and you need to consider those within the software. We will also look at these, and we will make reductions to shear perimeters to cater for these. And we're doing some quite smart things here in terms of how they are considered. So I've just sort of summarised some of the key considerations that we're going to look at with relation to flat slab design. I think what I'll do now is just get into the software and show you. So I've got a model arrangement here. Now I've imported this as a CAD file, and I could bring in my grid lines and my layouts directly from a reference drawing. And at this point, I'm going to start I've already established my column positions and the like, and at this point, I'm just going to take this and start to create my slabs. Now to do this, I can key in my thickness, so I might start with a slab that's 275 thick. Okay, and I can also come and define my load. So I'm going to put in my superimposed head load. And if I'm not sure about live loading, there's guidance here based on the code that you can draw from. So I'm going to assume that this is an office building, but obviously we can manipulate that. Now the loading can be, the way in which we insert slabs can be done in a number of ways. So you can insert by, if you had a frame model, it'd be by beam region, but I'm going to choose axes region to come and create my slab panels. You can also pick axes and pick points to create these. So let's just start to put in some slabs, and you can see here I've just created some slabs there. If I hit a control, I can just choose a panel and create a slab. Now as you're going, you don't worry about the yield lines that are getting created here. We're not interested in those for this example. Okay, I'm just going to run around and create my slabs as I go. So they're being defined by the axes boundaries that we've created. If you've got curved positions, they can be created by defining things like curved grid lines to set these out. Okay, you can, as you go, make changes. So if I decided that maybe in another part of the building the live loading is a bit higher, we can come and define those as well. So let's just run around and we can put our slab loads in. Okay, slab panels in. So I'm just coming here and defining a few more. Let's just quickly create these. Okay, and I'll hit Control again and put a panel in here. And you will establish your panels in a way that's sort of looking at bays. Okay. Now the reason why we do this, and instead of it being us creating one entire panel, is that obviously we have the importance of having to consider things like pattern loading, and I'll get to this shortly. So I've come and created a zone here. I can at this point come and check this, so I can come and use my visual interrogation manager to check my basic loading. And you can see here for the live loads there, I've got 2.5 and 3, so I can just visually check to make sure that's okay. What I can also do at this point is I may also want to check my pattern loads variations. Now, if you click on this, you can see that we will define different pattern load variations in Plant. And you can see the different variations here that can be used by the software. Now, this is quite a smart way of being able to pattern load panels. And now, traditionally, you may have been making adjustments to your pattern loading to take into account the effects of this within the design. Typically, with FE analysis, this is not available. But in here, you can make adjustments to these. And you can. This is a checkerboard, so you can turn pattern load variations on and off. So if you wanted to make adjustments to look at different patterning, these can be easily defined. And the idea here is that we can create a checkerboard here of the different permutations that you may come across within a project. Okay. Now these can be numerous, and so we give you the control with how you may want to set this up within the model. Now, at this point, I may want to come and add a little bit of additional loading into the project. So I'm going to come and create some wall loads. And to do this, I can just come and grab, say, a block wall, and I'll type the height of this in. Let's just assume that it's about 2.7 meters high. And we can then run around the perimeter of the model here, and we can come and create those perimeter loads. So here I'm just coming and putting in our loading. Now you'll notice that I'm covering multiple bays, and the software has just advised me that to consider this properly, we need to use finite element analysis. So you can be as accurate as you want with this. You can see that I'm just loading to the face of a column or wall, or I can pull the loading all the way through. This is entirely up to me. We can just come and set this up to suit. Okay, so I'm just running around here. Let's put these perimeter loads for the walls in. Okay, let's go to there, and I'll just finish this off. Just give me a few seconds, and we will be done. So again, this could just be my perimeter wall. Okay, you can do a similar thing with your internal partitions and just apply that loading to the building. So we'll run around a few more, and I think we're done. Okay, I think that's the last one. Okay, so you can see here I've just come and created that loading quickly. Okay, there's other things that you could consider in here as well. So maybe I've also got a plinth that I want to include, or maybe some local loading within the slab. That can also be defined here. You could also come and introduce some other things, other considerations that you may have within your building into the model here. So one of the considerations I touched on earlier was openings, and I'm going to just come in here and let's just create an opening that might be for services just adjacent to that column there. You may, as part of the model, and I'm just sort of trying to tighten up my architecture, do other things within the model. Okay, you may have openings for things like walls in here that you wish to define. Okay, I could just come in and do that. Maybe I want to put an opening in the wall there, and I'll just adjust the position. Okay, so these types of things can easily be adapted within the model. Now at this point, I'm just going to show you a 3D view, and so you can see here that I've created what is a subfloor at this point. So you can see my floor view, my walls, as well as my partitions. I've got a few column drop head panels there. Okay, they can easily be created within the model. Okay, if I just look at the properties of any column, okay, you can also come and add those in here, so you can feed the dimensions of what you want to create for the drop heads, and they can be included as well. Okay, so you'll just choose the zones where you may think that they may be of consideration, or starting point might not to be include them at all. Now I'm going to come in and let's just come in and generate some stories. Let's make this a let's just come in and insert a few floors. Let's make this a 4-story high building, and we can come and just generate that upwards. So I'm going to take that floor and we're going to copy this up the building. So let's just generate this information up. You can choose what you want to copy. If you didn't want to copy some of the slab loading that we had defined, that could be removed. It's entirely up to you how you want to do this. So you can see here I've created up to 4 floors now. Now I'm just going to come and select the roof level there because I want to make some changes to the model. Okay, and I'm going to just come in and tidy this up. So I'm going to remove my slab openings and my slab loads for the roof there. And I'm just going to assume that I've just got the live load acting there on the roof, and that may be sufficient for this example. So I've quickly come and created the model here. You can see, I've got a few openings in the walls. You can come and visualize the model here and just make sure it's what you would like to proceed with. I'm going to just at this point save the model, and the reason why I am doing this is that I want to start to populate the geometry, and I'm going to use this for looking at creating wind loading. Okay, so I'm going to save the model here, and the software will then be able to establish the extents of the building, and I'll then be able to apply my wind loads to this. So just give it 1 second and we'll be done. Okay, and then we can carry on with looking at the moving into the analysis and design processes. So we're done now, and let's move in and start to look at how we might go about analysing and designing this. Now today's session I'm designing this to the Eurocode, so you can select the codes of practice that you wish to use. You can also come in here and predefine the grades of concrete and steel that you may wish to employ within the project. Now I'm also going to establish my combinations here, and I'm going to come and generate. Now earlier you saw me create some pad load variations. I'm going to set those here as well. Okay, and I'm also going to create an unfacted case because I may want to look at unfacted deformations. Okay, and I'm also want to establish my wind loading cases here. So wind loading and notional loads, which are considered concurrently to the Euro code, are also created here. Now, if I hit OK, you can see that the software has generated all these different combinations automatically for me. Okay, so if I hit OK, that's been established. I'm going to look at the model options for the building now. I'm going to assume that my walls are going to be meshed. And I can also come in and for this example, I'm going to assume that all my slabs are meshed as well. So I'm going to mesh the entire building, walls and slabs. Now I'm going to turn off the diaphragm. So I'm going to assume that the slabs are going to act as diaphragms, and the stiffnesses of the slabs, in-plane stiffnesses, can be managed here as well. Now, the other interesting thing I'm also going to do is I'm going to assume that the column sections are going to be present in the FE model that we generate. So I'm going to create boundaries around the edges of the columns when we mesh, and that will be included within the analysis. So once I've established this, I can then just move in to look at the analysis and design. I'm going to run this. You'll just have to bear with me. It will take about a minute. Okay, and we can get straight in and perform the analysis here. So it's going to establish the model. Just give it 1 second. It's just saving this away, and then it will move into this process. Now, pre-analysis, you can check the model to make sure that you haven't made any silly mistakes with the modeling. So if you have axes that are perhaps clashing, maybe you've made some mistakes with how you've applied your loading, the pre-model check will help establish and check that for you. Okay, so these are quite sophisticated checks that we do to the project before you proceed with the analysis and design, and this will often trap out any issues that it may find. So just give it a second. It's just gearing up. My computer's not the fastest in the world, as you can see, and it's now moving through and running the analysis. So we are pre-preparing all the data here. Okay, it's the beauty of the way that this post-process works is that you can see the stages that it's going through in terms of establishing the analytical model, how it's going about creating the stories, the meshing. Okay, those types of things are all documented here, so you can see step by step how that process is evolving. Okay, and if you did have some considerations during this process, if the analysis did terminate at some point, then you have a record of what's occurred prior to that. Okay, so it's just completing the meshing, and then it will move into actually including the data preparation and moving into the actual analysis. So that's almost done. Give it a second. Okay, and we're now at a point where we're running the analysis. Now, for the analysis, we have the options of a skyline or a sparse solver. Sparse solver will in essence be faster. There's two different types of solvers, and you may ask why. Skyline solver allows us to interrogate the data more rigorously post-analysis. So if there's issues, Skyline solver provides more background, whereas a sparse solver ignores a lot of information as it progresses. So even though it's faster in terms of interrogation post-analysis, if there's issues, it doesn't provide us with as much information. So this is done, and we've also checked concurrently the inter-story drift checks, which has satisfied the code, and we've now completed the analysis. So if I close this, I can then take a look at the post-analysis results, and I'm just going to quickly look at this within the context of our 3D post-processor. Let's give it a second, that will load this. Okay, and then we'll be able to review the results. So here you can see the model. Okay, I've meshed the entire model here, and we do some quite smart things with the meshing. Now, I don't know if you can clearly see my model here, but the way in which we mesh boundaries is very important, and we will mesh them so that you can see all the nodes are matching. Okay, so the slabs will meet the wall nodes, and that will provide an effective transfer for our stresses. Now I can start to look at various results in here. I may be interested in looking at the analysis results for, say, axial load. Okay, I can come and interrogate those. You can see those results clearly there. If you wanted to just filter out a floor, maybe I'd just like to see the first floor, for example, we can come and look at that in more detail. Now, the other thing that you might notice here is that we've also meshed to the boundary of the column. So the actual extents of columns are provided, so whether they are circular or square, or whatever shape, we will build rigid arms within these zones and we will mesh to the faces. And this can provide you with an additional degree of economy and perhaps a more accurate model in terms of looking at behaviour. I can, within here, take a look at some preliminary contours, okay, and we can look at the behaviour of the slab as part of the overall building if we wish, okay, and you can see those results here as well. But maybe what I want to do at this point is just come out from here and we may want to look at and individually look at this in more detail. Now at this stage I can also get straight in and we can design the columns and walls. So right now, before I even move into looking at the flat slab design in more detail, I can start to produce information from this. So we've included the slabs and model in one complete model. We've looked at all the local behaviour there of the structure, and we can now move in and start to design and even start to detail some of these elements out before we get too far. So you can see there it's just finishing off the column design. Just give it a sec, it's quite quick. We've done nearly 160 odd elements, and they're all designed. So I think you can see there that all the various checks for the columns have been performed. If you want to look at the status of the column design at any point, you can go back to the visual interrogation and you can have a look at this. So if I'd like to see, okay, whether everything's been designed there, I can just click on that and you can see that they're designed. Now, even at this point in time, okay, I may want to do some preliminary documentation of the model. So to do that, I could just go straight out to Prota details and we can start to create some output from the model, okay? So it'll just save this and it will launch Prota details. Maybe we are just wanting to provide some preliminary information to site. We may be wanting to just start construction processes where we may have designed the foundations as well, and we're providing the first story column design to get the project going. Okay, at any point you can come and start to document out from the model. So I'm just going to show you a little bit of this within Prota details. Prota details is not the focus for today, but I just wanted to just bring it in to show you how some of this documentation might start to happen. Okay, so Prota details is launching, okay, and then we can then start to produce some of the output. Okay. So I'm just going to automatically generate some of this. Okay, let's just choose to create some basic information. I'm going to set it to sheets, and then we're just going to ask it to draw. So it will just come in and we can draw up information that we have just been creating. Okay. So you can see it's populated here with my title block, and it's now starting to prepare some of that background information. So at this point, we may want to create some key plans. We may just want to create our column detailing and wall detailing. This can be generated out at this point in time. Okay, so not to slow the overall design of the project down. So just give it a second. A few more columns, walls are being created, and then we can have a quick look at the output here. Okay. Okay, so here you can see that we've come and created the key plans there. You can see my column drop head panels, my core walls and the like are being drawn. They've been nicely placed into title blocks. And you can also see things like set out plans, so you can see column and wall details there. They can be placed in title blocks if you wish. Okay, and you can also see our elevations there together with that little opening that I created in that wall earlier. So this is just some of the output that you can expect from the system. Now let's get back into the Prota structure model, and let's start to look at things in a little bit more detail. What I'd like to do at this point is let's just move down to the first story plan, and I'm now going to come and run the finite element analysis for this floor. Okay. Now, pre-analysis, we need to establish some conditions here, and one of the important things that I alluded to earlier was cracking and creep. Now, to do this, we can consider this within the model. So, and we are referring to that earlier guidance that I alluded to, where you can key in basic typical dead loads. You can also key in your typical live load, and then we will give you an estimate of the suggested range to consider for crack and creeping. Now, as I said earlier, it is very subjective, so it will depend largely on the nature of the structure. If you've got, if it's used for storage, for example, these factors will be higher. If it's used for office and domestic use, then these range will be lower. It'll also depend on the quality of construction, how you're propping, all these types of considerations. But as a general guide, there's a recommendation here of adjusting the factors between 0.28 and 0.31 of our EI value. So for this one here, I might use 0.3. Okay, I might accept that, and we will then make those adjustments to the stiffness factors. Now at this point, I can then come in and we can mesh the slab. So it's now going to take those properties and we're going to mesh just this floor as a subframe floor. Okay, and you can, if I just click on meshing, you can generate the mesh. Now what you can do also is you can play with the mesh uniformity. The meshing is adaptive, and you can look at adjusting element size here to provide you with a more dense mesh or less so, depending on what your requirements may be. But the meshing is adaptive, so you'll notice as you get closer to things like column heads, the meshing will be more tightly spaced, and as you get to mid-span, the meshing will be further apart. Now people might ask us also, well, why are we using triangular meshes here and not, say, quadrilaterals? Well, the answer is that, especially when you get to things like column heads, you will see that the moments are increasing, and we need to be able to interpolate between points. So with a triangular mesh, it allows us to do that and allows us to trap out peaks. Whereas if you have a quadrilateral mesh, that is not so effective, and trapping out those peaks becomes more difficult, and sometimes you can miss them. So this is why we tend to use triangular, or you could use a combination of triangular and square meshes within the slab, and we use square meshes within the walls, which are more effective at dealing with shear. So I've now generated that model. If I just close this down, it will then run the analysis, and it will then perform the stress analysis for this particular slab. So we're just going to run it as a subframe, and we can then come and have a look at the results. Now, if you did want to make adjustments at any points to things like moments, okay, you may not be entirely happy with, say, the catering for all the different pattern load variations. You can make adjustments here, so you may wish to adjust perhaps the negative or positive moments accordingly. You can make adjustments here if you want to introduce a degree of conservatism. Okay, this is up to you, but that's available here. I'm going to then, at this point, just come and have a look at the output. Now you can see here that we've meshed it, and you can see that I've got some quite exaggerated displacements on view there. Okay, I might just reduce those, and I'm going to have a look in particular at the service cases. So you can see all the different cases as well as envelopes on display here, and you can just choose what might be appropriate for you to review. And I'm going to have a look at some contours. Now I can look at this in a 3D perspective, or we could look at this within the elevation view. And you can see from here that obviously this zone off to the top left here is where I have the most excessive deformations. Now in this scenario here, I've got a deformation of 23 millimeters as an ultimate long-term displacement, and I may or may not be happy with that level of displacement. This is up to you. And you can, in here, you could come in and provide user-defined contours to map maximum allowables that you may wish to establish. So let me just, I'm going to use a threshold contour here. Okay, and I could say that the maximum displacement within the slab that I would like to accept was 20 millimeters over that period, and it will then move in and can show you parts of the slab where that may be exceeded. Okay, so it's not a exact science. Obviously, it will depend on the spans that you're looking at. Okay, you would need to use some engineering judgment here as to what you would consider to be acceptable. Obviously, in accordance with reading the code guidance for the type of building that you're designing. Now, another way that you can look at deflections is you can use strips, and I can just cut a strip through this part of the model, and the deflections along that strip would then be resolved, and you can see here a displacement, and you can see that my displacement of 23 millimeters is indicated there for my dead plus live case. Okay, so I may be happy with this scenario given it's a long-term case. Maybe I've also introduced a bit more propping, so I may be happy with this scenario. This is entirely up to you. Now, along the left here, you'll notice that in addition to looking at displacements, we can also look at other effects. So I may want to look at what the moments are on the slab. Okay, and then here you can see moments in the X direction and the range of moments that we have, as well as in the Y. You'll also notice that there's MXY moments, and these MXY moments are torsional moments. So these are our wood armour effects or torsional bending within the slab. Now, what we do is we will take these wood armour effects and we will resolve these into X and Y for design. So you can look at both moments globally as well as locally, and these will just be orientated differently depending on what you want to see. But you'll also notice here that there are design moments, and the design moments are broken into moments in the X direction in the bottom, okay, which you can see, and moments in X direction and Y direction in the bottom, and you can also see moments in the X direction in the top, as well as in the alternative direction. So in here, you can come and view these to give you a feel for peak moments that you have within the slab. Now, the final interesting thing here is that we also concurrently have our area of steel contour plots. And I may wish to look at the area of steel contour plots, and I'm going to look at the maximum envelope of these within the slab. Okay, so here I can see that I have a range of steel from 0 up to 1,015 millimeters squared per meter. Now, we may also want to make adjustment for the slab. So these area of steel contours are actually calculated based on us predetermining a concrete cover, as well as a basic steel bar size. Now, I might be using as a minimum 12 bar in this project, so I can come and set this here, and we will then adjust in X and Y directions. We will adjust the effective depths to be considered for looking at area of steel requirements for bending. So if I just make that adjustment, you may just see that very slightly these diagrams have changed. Now, what do these mean, and how can we interrogate these results? So here I can see this range of steel, but what does that actually mean in practical terms? Well, what the advantage we have within our Prota structure is we can start to use these, and we can use these to lay out predefined contours. So again, I'm going to choose my user-defined contour plot here, and I'm going to come to edit contours. Now, in the edit contours here, you'll see that I've interpolated a range of different contours. Now, depending on the scale of the moments and forces in the slab, you may wish to have more contours. This will be entirely up to you, depending on the nature of the project. But you can, at this point, use this to help predefine some basic steel. Now, I may decide that for my bottom steel, I'm going to have a minimum bar arrangements of maybe H12s at, say, 250. that might be my minimum steel that I'm going to use throughout this project. And I'm going to ask it to create an interpolation line based on this criteria. Now, you can see that that's covered almost all the slab here. There's just a little bit that's not covered. And I may decide that for those other zones, I wish to use a little bit of extra steel. I'm going to use maybe one layer of 16s at 250. And I may have another layer of, or we may keep the same layer of H12s at 250 as well. Okay, so if I update this, you'll see that now this is providing me with a, oops, let me just check that, make sure I've got that checked. Do that again. Okay, so you can see that this range of steel here is slightly more than the maximum required in the bottom and the X direction. So if I hit OK there, you can see very clearly now that I have a baseline steel, which is the 12s at 250, which is being used throughout the bottom in the X direction. But locally in the green zones, I need a bit of extra steel, and this is where I need my H16s at 250 plus H12s at 250, and these may be alternating bars at 125 centers. So I know exactly the location of where that reinforcement may be required in the slab here. Okay. Now, if I wanted to, at this point, I could export these contours, and we can then view these contours on top of a model within Prota structure, and we could interpolate from those for laying out our reinforcement. I can look at this in other directions, so we could also apply the same thing for the other direction in the Y, and we could do this. But when it comes to looking at things in the top, you may notice that we've got a much higher peaks of steel that are occurring. Now I'll just turn off the envelope and let's just look at a combination. Okay. I'm just going to look at the standard contours. Okay. But what you may notice that when you come in and interrogate the diagrams here, you'll notice that when you get close to column heads, you can see that the moments are peaking. As the moments peak, you obviously need additional steel across those zones. Now, if I had to take the absolute peak, which is right at the point of, say, this column here, that may be very high. So you can see in this zone here, it's asking for something like 23,000 millimeters squared per meter. But the code generously allows you to average across those strip widths. And this is what I was alluding to earlier, where there's an empirical approach that you can use to consider this. Now, what you will do is you will look at the spans that you have either side, and the code will provide you with guidance as to the strip widths that you need to consider for design across these peaks. And to do that within the software, we can come in here and set bandwidths. Now, if this was a span of 8 meters either side, I may set a half bandwidth of something like a meter. Okay, I think in my situation here, I've got slightly less, but I'm going to take 750 millimeters either side of this column here, and this may be the maximum column head that I'm looking at for this zone. I know that there's other peaks. These peaks are isolated to the walls in this scenario, but I'm just going to choose this, which may be the maximum in my model here. So I'm going to come and draw. I'm then going to come and choose to draw a strip. Okay, and I can come and choose a strip, and I don't just need to go through one column. I could choose to interpolate across a number of column heads there, and I can then use this to start to look at what might be the effective design for the steelwork across those column heads. So here you can see it's creating our integral strip. Okay, and you can see the strip results that have been created here. Now there's two strips that we're cutting here. We're cutting a peak strip, which is the normal strip, and you can see that the peak moment that I have there is something like, I think, 320 odd. And that can, and I'll use the design moment because this is where we are looking at the wood armor effects. And this peak moment would result in us requiring about 2,050 square millimeters of steel per meter width. Now, obviously that's very high, and as I mentioned, the code allows you to interpolate across this strip width here, which is what I'm going to do. So I'm going to use an interval strip, and we're now integrating across the strip width, and we're flattening out these peaks. So the code will allow you to do this, and you can then work out a more economical arrangement for steel. So I require about approximately 1,500 square millimeters of steel for that. Okay, and if I have done my math right, that may be something like 16s at 250 across that head. Okay, so I could then use this as a methodology for providing the design across those column heads. Okay, so I've taken the peak, I've used interval strips, and then I'm now predetermined that for most of the column heads within this building, I'm going to use 16s at 250 based on these strips. Now, you will, the beauty with using the finite element analysis is you can set up these support band strips and mid band strips wherever you like. So I will have naturally different requirements for other parts of the model, but you can just cut these strips wherever you like. And you will also notice that if you come to, say, wall locations, you may have higher localized stresses, but again, you can see that quickly these are diminishing. And by taking advantage of the interval scripts, you can then plan out the reinforcement that you may require in these zones. Okay, so that's one way in which we can interpret the design, and we can come up with a sensible design for looking at the flat slab. So we can use area of steel contours, we can take advantage of integral strips, and we can also take advantage of user-defined contours, which we can extract back to our model for refinement as part of the detailing process. So I may at this point just be happy with that at this point. Okay, and I now want to come in and look at the model in more detail with respect to other considerations. So we may have designed our steel, we've got our baseline steels, we know what's in there, we know what's in the peak across the column heads, which is say 16s at 250. I now need to come in and look at punching shear. Okay, and in here we can come and select columns. You can choose the whole floor plate if you want to, but I'm just going to maybe look at these as an example. And within the software, we can ask the program to check for punching shear. Right? Now it's looking at the perimeter, and these are internal columns, so I'm going to be checking these as an internal perimeter. We can also check the column drop head panel perimeter, because locally within the drop head, as you get to the edges, you may have additional local shear stresses or changes in shear capacities there, which you may also want to check. So we can also consider this. And I'm going to define in here the slab rebar that we have. So we have 16s, okay, and they're being spaced at approximately 250 is my maximum. Okay, and we can come and set this, and I'll do, let's just assume in both directions the values are the same. And let's just change this as well. So let's go for 250 or so. Okay, so I've set these up, and then I can then just ask it to design this. Okay, so it's now checking the design of those zones, and the software will at this point provide a report. So Protostructure will generate a report now, and it will provide you with all the underlying checks for the punching shear. So we're doing a number of checks here. So we're checking at the face of the loaded area, and depending on the code, we're also checking at either 1.5D or maybe 2D away from the face of the column. Now, earlier I mentioned to you that there are adjustments being made here to calculate our effective shear, and this is based on the biaxial moments that are also present in those columns. So this is based off the frame action that may have occurred from the building analysis, and being able to mesh the building, mesh the floors and within the building, and provide a comprehensive building analysis with all the localized stresses is also being taken into account here. And you'll see that it's then checking these parameters and it's ascertaining whether or not we need to provide any additional shear steel. So all these checks are done for those columns, and I think in this situation here, these have all passed, and you can see the detailed checks and code clause references there. Another interesting thing that we've also done here is you may see that we have, even when we have openings in the slab, we are adjusting the shear parameters, and these can be automatically adjusted, and we will reduce the shear parameters here as well. Now, if you found that for this particular column, okay, I wanted to change that further, I can come in here and manipulate this further. So if I decided that shear parameter was, I wanted to use a larger parameter or make a bigger reduction, I can make those adjustments here as well. Now, what about other zones? Maybe let's come over here and look at this edge column here. Again, if I just select the column, you can just individually go in and check a particular column here. I'm going to check this parameter, and I'm also going to look at the punching parameter, and I'm going to choose the edge location. Now, just be aware that we're not automatically working out whether it's edge or corner or internal. You do need to do a little bit of work here to create these. So just choose the appropriate column location. And obviously you'll predefine the steel that may be provided there locally. Okay, we could maybe assume 16s at 200 or something. Okay, and then we can then design for this parameter. Okay. So what you might notice here is that this parameter has not actually satisfied the code. Okay, and from the checks you'll be able to see that in this locality I do need a bit of extra steel, okay, and we've then defined the amount of additional shear steel that you would need to provide, and these can be provided in the form of links. They could be studs that you include, or you could look at increasing your maybe longitudinal bars to see if that will help this pass. But what we are doing is we're checking these parameters in detail, and we are providing you with localized requirements in terms of providing that additional steel. And there's quite sophisticated checks being carried out here to determine those parameters and perform those design checks. So I just wasn't going to go into a lot of detail today. Well, I have, I guess, but I wasn't going to go into a lot of detail in terms of designing the whole building. But I just wanted to give you a flavour and some insight into the type of considerations that you need to be aware of if you're designing flat slabs. And all of this we can do within the Prota structure model. So so if you just bear with me, I'm just going to conclude. So we do have comprehensive treatment for the design of flat slabs within Prota structure. Models can be easily created, as you saw. You can make considerations for very irregular arrangements. You can introduce things like drop head panels if they are required. You notice that I put the panels in to suit the way in which I wanted to carry out my pattern loading. Okay, and we will perform full FE analysis. That could be for the entire building, or you can look at it on a subframe basis for looking at local treatment and maybe looking at long-term creep and shrinkage effects, which I covered. Now, within this, we are making considerations for things like pattern loading, frame action with the entire model, where we're meshing the slabs together with the columns and walls and looking at the localized stresses and actions around those. We can make detailed considerations for creep and shrinkage. I took advantage of using integral strips to work out what my maximums may be for across my column heads, as well as also looking at area of steel contours for defining rebar arrangements. And I concluded there with looking at the punching shears, and that can also look at considerations for openings. Now, obviously, all this can be documented out, so we can provide all the design reports out to and compile those into one document, and we can take the output out into Prota details. We don't provide complete detailing for flat slabs at this point. You could understand that if you've got column heads, you've got quite difficult rebar arrangements in those, but needless to say, or watch this space, there is work being carried out in this area in the future. So in the future, you will be able to see all the detailing being carried out across those zones. Now, further guidance. Background notes with today's presentation will be made available with the webinar recording. So if you go to our YouTube channel or you want to look at and you want to find out more, we can make available more information. For existing users, a lot of this information is already available in our Knowledge Hub. Okay, so please take a look at that. Okay, please take a look and refer to information there. Okay, now just to conclude and just give you some background, what I've shown you today has been used on numerous other projects around the world, and we have used it actively on some of our projects. So here you can see we did take advantage of this with the new international airport, as well as some of the universities that we've recently designed. And you can just see some of those models here where we've got flat plates, particularly for things like roofs that we've employed. Okay, here's some other models, flat slab systems being used in Singapore. Okay, here's another interesting project in Turkey where we've designed flat slab systems. Okay, and you can get into some really huge systems with things like transfer plates and the like. We are obviously supplying software to a range of interesting businesses around the world. It really is a fantastic period for us as we grow to engage some of the other leading consulting businesses worldwide, as well as our fantastic user base, ranging from one-man bands up to some very eminent businesses. I think the key behind solution is that it's just not about building design. Yes, that's part of what we do, but our vision is that we're going end to end. So we are going from modeling, analysis, modeling, and design, right through to full documentation. And that includes all the drawing management, all the drafting capabilities, component design. You may have seen that within earlier webinars with Prota details, as well as being able to provide you right down to fabrication detailing. So whether that's rebar schedules or steelwork fabrication detailing, breaking out things like connections and providing you with all the shop drawings. All this is part of the platform that we've been working very hard on over the years. Now, I think increasingly we're seeing many of our clients are starting to interact with other project team members, and BIM collaboration is also becoming increasingly important. And this is also a key consideration with how we have developed the platform, being able to share that information out with others. So I invest significantly in development. Obviously, I've presented today, so I should have adjusted that, but I really would love for those of you who have joined today to also join us on the 24th of June. We've got something really special coming. I'm not going to let too much out of the bag, but this is something that we've been working on for a number of years now, and that's coming to fruition, and we are very, very excited to be able to introduce to you next generation technology. So if you are available, put that date in your calendar. We are going to be, there's something exciting that's happening that I think you don't want to miss. So thanks for attending today. To our users, thanks for your continued support. We really love the feedback that we get from using the product. We've got a really fantastic user base, and they actively engage our support teams, and we really love working with them to realise their projects. For those of you who are new to the system, we do actually have some special offers at present. They are concluding, so if you are interested in, I guess, the COVID offers, they are available at present. Please, as you head out, please answer the survey, and if you are interested in finding out more, let us know. You can also email us directly through our channels at global sales at prosoftware.com or Asia sales at prosoftware.com, and we will help you out. Please follow us as well. We are very active on YouTube, Twitter, Instagram, and the like, Facebook, LinkedIn. So connect with us, and we will be able to share with you a lot of what we're up to at present. So on that note, I'd just like to thank you very much for your attendance today. It's been great having you. So sorry we had a few glitches along the way, but I think at the end we've covered quite a lot of ground, and it's been a interesting session. So on that note, I'm going to finish the session, and we look forward to continuing with these technical engagements and also delivering interesting technology in the years to come. So thank you very much.